18,900 light-years from Earth. A star so massive it could swallow the orbit of Saturn whole is burning through its final breaths. Inside it, 2,150 suns could fit, side by side. We're going to meet a star that rewrites the rulebook, dust clouds that hide a sleeping giant, and a countdown to one of the biggest explosions in our galaxy. If your jaw is already on the floor, smash that like and subscribe. It really helps. Lights down, headphones up. Let's begin. Step outside on a summer afternoon. Look up. The sun feels enormous. It heats your skin, lights up entire continents, and has bullied every planet in our solar system into orbit for almost 5 billion years. Our sun is so big that 1,300,000 Earths could fit inside it. That number alone is hard to picture. You could pour every ocean, every mountain, every desert into the sun over 1 million times before it filled up. And yet, on the cosmic scale, our sun is a speck. Somewhere in the constellation Scutum, hiding behind a thick veil of cosmic dust, there is a star so impossibly large that the sun next to it looks like a single grain of sand on a stadium field. Its name is Stephenson 2-18. Astronomers also call it Saint 2-18 for short. By current measurements, this star has a radius around 2,150 times bigger than our Sunday. 2,150. Try to picture that. If our sun were the size of a basketball, Stephenson 2-18 would be a sphere wider than the entire Eiffel Tower is tall. Wider than 30 Eiffel Towers stacked end to end. Wider, in fact, than most cities you've ever driven across. And it is still a single object. A single, glowing, fusing ball of plasma held together by gravity alone. Here is where things get genuinely strange. If you ripped our sun out of the center of the solar system and dropped Stephenson 2-18 in its place, every inner planet would be gone in an instant. Mercury vaporized, Venus vaporized, Earth vaporized, Mars vaporized, the asteroid belt vaporized, Jupiter vaporized, Saturn vaporized. The surface of this star would extend somewhere past where Saturn used to orbit. Everything we have ever known, every photograph ever taken, every footprint left on the moon, every word ever spoken, would be inside this star. It is a confirmed red supergiant. Scientists are still debating exactly how big it is, because measuring a star this far away through a fog of dust is brutally hard. Some teams argue the size could be smaller. Others think it could be bigger. The leading number, published from Australia Telescope Compact Array data in 2012, still holds 2,150 solar radii. What we know for certain is that this star exists. It is glowing, it is dying, and it is changing what we thought stars could even be. But here is the question that haunts the astronomers who study it. How did we miss something this enormous for so long? It sits in our own galaxy, not in some distant universe billions of years away, right here, in the Milky Way. And for almost all of human history, nobody had any clue it was there. Telescopes pointed at that exact patch of sky and saw nothing remarkable, just a faint red smudge hidden behind clouds of interstellar dust thicker than smoke. The story of how we found it is wilder than the star itself. It involves a forgotten astronomer, a misunderstood star cluster, and a technology that finally let us see through the dust. That story starts next. Your brain is a remarkable instrument. It can recognize a friend's face from across a crowded street. It can imagine a purple elephant playing chess. It can do calculus, write poetry, fall in love. But there is one thing your brain absolutely cannot do. Your brain cannot picture Stephenson 2-18. Not because you are unintelligent, not because you haven't tried hard enough. The human visual system literally evolved to handle objects somewhere between the size of an ant and the size of a mountain. Anything bigger, your mind shuts down and just stores it as a label. The Earth? That's a label. The Sun? That's a label. The Milky Way? definitely a label. You think you imagine these things. You don't. You imagine cartoons of them. So let's try something different. Forget the actual size for a moment. Let's shrink everything down by exactly the same amount and see if your brain can hold on. Imagine our sun shrinks to the size of a grape, a small green grape sitting on your kitchen table. At that scale, the Earth becomes a poppy seed, about 30 feet away across the room, maybe out the window. Mars is another tiny speck a bit further. Jupiter, the biggest planet in our solar system, is about the size of a marble, and it sits 150 feet from the grape. That's already half a football field. Now, at that same scale, where is Stephenson 2-18? It would be a glowing red ball roughly 400 feet across, bigger than a football stadium, taller than the Statue of Liberty stacked 3 times. The grape, our entire sun, would be a tiny green dot inside that red ball, completely lost. Your brain still isn't picturing it. It is just nodding along. That's okay. Almost no one can. Astronomers themselves admit they don't really visualize stars this big. They work with numbers, ratios, equations. They calculate, they simulate. But when you ask them to honestly imagine standing next to Stephenson 2-18, most of them laugh and say it's impossible. The scale breaks the imagination. Here is something even weirder. If you tried to fly around this star in the fastest jet humanity has ever built, the X-15 rocket plane that hit 4,500 miles per hour, the trip around its surface would take you over 200 years. You would die of old age many times over before you finished one lap. A photon of light, the fastest thing in the universe, takes nearly 9 hours to travel around it. Around our sun, light makes the same trip in 14.5 seconds. This is not a number you intuit. It is a number you accept on faith from physics. And here is the part that will keep you up tonight. Stephenson 2-18 is not even guaranteed to be the biggest. There are candidate stars hidden deeper in the galaxy, behind even thicker dust clouds that might be larger. The James Webb Space Telescope is starting to catch hints of them. Stars so massive that current physics says they shouldn't exist. So how did anyone ever spot Stephenson 2-18 in the first place? The answer involves a single faint photograph taken decades before anyone realized what they had captured. 1990, a quiet observatory in California. An astronomer named Charles Bruce Stephenson is sorting through infrared photographs looking for something specific. He is hunting star clusters hidden behind the dust of the Milky Way's inner disk. His eyes are tired. The work is tedious. Most photographs show nothing interesting, just static and noise, and the same kinds of stars he has seen 1,000 times. Then he stops on one frame. There, in a region of sky most astronomers had ignored for decades, is a tight knot of red giants, dozens of them, all clustered together, all glowing in the infrared, all hidden from regular optical telescopes by a wall of interstellar dust so thick it had been blocking the light for thousands of years. He names the cluster Stephenson 2. It becomes the second of several similar discoveries he will make in his career. At the time, no one realizes that one specific star inside this cluster, a faint red dot on the 18th row of his catalogue, will eventually become a candidate for the largest star ever measured. They just call it Stephenson 2-18, a boring catalogue name for what would later turn out to be a monster. For over 20 years, nothing happens. The star sits in the database. Other astronomers occasionally glance at it. Nobody thinks much of it. Why would they? It's just one red supergiant among many in a crowded cluster. The real action in astronomy is happening elsewhere. Exoplanets, black hole imaging, dark matter searches. Then, in 2012, a team using the Australia Telescope Compact Array decides to take another look. They are studying the entire Stephenson 2 cluster, trying to figure out exactly how massive these stars are. They pull data on each one, they run the numbers, and when they get to Stephenson 2-18, the calculator gives them a result they don't trust. 2,150 times the radius of the Sunday? They run it again. Same answer. They check the distance 18,900 light-years away. They check the brightness about 440,000 times more luminous than our Sunday. They check the temperature only 3,200 Kelvin. Surprisingly cool for something so bright. The math keeps giving them the same impossible result. This star is bigger than current physics says it should be allowed to be. Stellar physicists have a rule, sometimes called the Hayashi limit. It says red supergiants can only get so cold and so bloated before they fall apart. Stephenson 2-18 sits right at that edge, maybe past it. The team publishes their finding in 2012, and the astronomy world quietly loses its mind. For years afterward, debate rages. Is the measurement correct? Is the star actually a foreground object that just happens to look like it's in the cluster? Are the dust calculations off? Is it pulsating in a way that makes it look bigger right now than it really is on average? The arguments are still happening. Saint 2-18 sits in our galaxy, glowing red, fusing elements in its core, oblivious to the chaos it has caused. And the closer astronomers look, the stranger it gets. If you stepped outside tonight and pointed your finger at Stephenson 2-18, you would not see a thing, not even with binoculars, not even with a backyard telescope, not even with most professional observatories built before the year 2000. The star would be sitting right where you pointed, but it would be invisible. It is not because the star is dim. Up close, it is one of the most luminous objects in our galaxy, pouring out the light of 440,000 suns, burning so brightly that any habitable planet within a few light-years would be roasted instantly. It is invisible because of the dust. Between us and Stephenson 2-18 sits a thick, grey-brown wall of interstellar dust. We are talking about the dust lanes of the inner Milky Way, the stuff you can see as dark streaks cutting across the bright band of the galaxy on a clear night in the countryside. Those streaks are not empty space. They are clouds of microscopic carbon and silicate particles, smaller than smoke, drifting in the void between stars. Visible light hits this dust and gets absorbed almost completely. The starlight of Stephenson 2-18 has been traveling for 19,000 years, only to slam into a fog bank and vanish in the final stretch. Infrared light, however, slips through. Infrared is the kind of light your TV remote uses. Slightly longer wavelengths than red, invisible to human eyes, but able to push through dust like sunlight pushes through morning mist. When astronomers point infrared cameras at the constellation Scutum, the dust melts away and a hidden universe appears. Star clusters that nobody knew existed. Glowing nurseries of newborn stars. Old red giants pulsing slowly. And there, in the middle of one of those clusters, Stephenson 2-18 finally becomes visible. The dust does something useful though. It dims the star in a predictable way, which lets astronomers calculate how far away it is. The more reddened a star looks, the more dust must be between us and it. By measuring the exact wavelengths of light we receive, scientists figured out that this star sits roughly 18,900 light-years from Earth. That distance is so vast it is almost meaningless. The light reaching your eyes right now left the star while humans were still building the first cave paintings. Here is the part that should give you chills. The dust is also a problem, a big one, because dust around the star itself, not just between us and the star, can fool measurements. If Stephenson 2-18 is wrapped in its own personal cocoon of dust, the way some red supergiants are, then the light we are seeing is being reprocessed. It might be coming from the dust, not from the star directly. The true surface of the star could be smaller, or it could be exactly where we think it is. This is one of the main reasons astronomers argue about the actual size. Without piercing the dust completely, we are essentially measuring a glowing balloon and trying to figure out where the rubber ends and the air inside begins. Newer telescopes are starting to crack the puzzle open. The James Webb Space Telescope, with its enormous infrared eye, has begun mapping these dusty regions in unprecedented detail, and what it is finding is not what anyone expected. Think about the light hitting your eyes right now. The photons from your screen left it less than a billionth of a second ago. Sunlight reaching your window left the sun about 8 minutes ago. Light from the moon just over a second ago. These delays feel small, negligible. Light is fast. Now consider a single photon currently entering a telescope, fresh from Stephenson 2-18. That photon left the surface of the star 18,900 years ago. Let that timeline soak in. 18,900 years. When that photon began its journey, the last ice age was still ending. Mammoths still walked across northern Europe. Humans had not yet invented agriculture. There were no cities, no written language, no metal tools. The entire population of our species lived in scattered tribes of hunter-gatherers, and the photon was already traveling at 670 million miles per hour. It crossed the empty void between stars. It passed through cold molecular clouds where new stars were just beginning to form. It threaded between giant suns and slow-burning dwarfs. It survived the gravitational pull of black holes, whose gravity bent its path slightly without trapping it. For 19,000 years, that photon raced through the Milky Way at the absolute speed limit of the universe. Meanwhile, on Earth, civilizations rose and fell. The pyramids were built. Rome conquered the Mediterranean. The Roman Empire collapsed. Knights rode in crusades. Columbus landed in the Americas. The Industrial Revolution happened. World wars came and went. Humans split the atom, walked on the moon, invented the internet, and the photon kept traveling. Then, in the last few seconds, it slammed into the lens of a telescope and ended its journey. That is what astronomers actually study when they look at this star. Not the star itself, in real time. They are looking at a snapshot from before recorded history began. Stephenson 2-18, as it appeared during the last ice age. Whatever the star is doing right now, pulsating, exploding, going completely dark, we will not know about it for another 19,000 years. Maybe it has already gone supernova. Maybe its core has already collapsed into a black hole. Maybe it has already vanished from existence. There is no way to tell. The star we see is a ghost, a delayed echo of an object that may or may not still be there. This delay is also why astronomy is humbling. Every photograph of a distant star is a kind of time machine. The Andromeda Galaxy, which you can see with your naked eye on a dark night, is 2.5 million light-years away. The light you see from it left when our ancestors were primitive primates not yet using stone tools. The supermassive black hole, imaged by the Event Horizon Telescope, sits 54 million light-years away. That image showed us light from the time when dinosaurs had only recently gone extinct. Stephenson 2-18 is much closer than those. It is in our own galaxy, and still, we are looking at it as it was almost 20,000 years ago. The really wild part? Whatever it is doing right now would absolutely change everything we think we know about how stars work, but we'll never live to see the answer. What it was doing 18,900 years ago, however, is shocking enough on its own. Numbers in astronomy are slippery. 2,150 solar radii. It rolls off the tongue, but it doesn't actually mean anything to a human brain. Let's translate it into things you can feel in your gut. Our sun has a radius of about 432,000 miles, a respectable size, big enough that if Earth were a marble, the sun would be a ball almost 40 feet across. Big enough that light, which crosses the entire United States in about 15 milliseconds, takes over 2 seconds to cross the sun's diameter. Now multiply that by 2,150. The radius of Stephenson 2-18 comes out to roughly 930 million miles. That number is so big it crosses out of solar system territory and into deep space scales. It is bigger than the orbit of Saturn. If our sun were swapped for this star, the surface would extend almost all the way to where Saturn currently orbits. Saturn's rings, those magnificent ice bands that took the Cassini spacecraft 7 years to reach, would be inside the star. Let me try another comparison. If you started walking at a normal pace of 3 miles per hour, and somehow you could walk on the surface of Stephenson 2-18 without melting or being crushed, It would take you over 200,000 years to walk around it once. That is longer than humans have existed as a species. You would need to start your walk during the early Stone Age and you would still be walking right now. Even at the speed of sound, the trip around the surface would take about 200 years. And yet, here is the surprise. Despite its enormous size, Stephenson 2-18 does not have very much mass packed into it. Its mass is somewhere around 40 to 50 times the mass of our Sunday. Compare that to its volume, which is roughly 10 billion times the Sun's volume. The star is shockingly diffuse. Most of it is closer to a vacuum than to a solid object. If you could scoop up a bucket of average star material from inside Stephenson 2-18, it would weigh less than the air in your bedroom. You could probably wave your hand through whole regions of the outer envelope without feeling much resistance. The atmosphere is so thin and so puffed up by radiation pressure that the boundary between star and space is genuinely fuzzy. This is the bizarre truth about red supergiants. They are not solid balls. They are huge, slow, glowing bubbles, mostly empty, mostly hot gas, mostly held in place by a complex balance between gravity pulling inward and pressure from nuclear fusion pushing outward. If that balance shifts even slightly, the whole star starts to wobble. Stephenson 2-18 is wobbling. The pulsations are slow. They take years to complete a full cycle. The star expands a little, contracts a little, expands again. Each cycle changes its brightness slightly, which is how astronomers know it is happening. Some months it appears bigger, some months a little smaller. It is breathing, in the way a dying giant breathes long, slow, shuddering breaths, and those breaths are leaking material into space at a rate that is utterly staggering. Imagine, for a moment, that we could perform a cosmic experiment. We yank our sun out of the center of the solar system. We replace it with Stephenson 2-18. We do not move the planets. We just swap the stars. What happens? In the first instant, Mercury is gone. The closest planet to the sun gets vaporized so fast it doesn't even register as a death. Mercury orbits at about 36 million miles from the Sunday. The new star's surface extends 930 million miles. Mercury is deep inside the new star. It is not orbiting anymore. It is part of the plasma now. Half a second later, Venus is gone. 67 million miles out, also deep inside the star. Earth, at 93 million miles, is gone. Every ocean evaporates instantly. Every mountain melts. Every living thing, every memory, every record of human civilization is plasma. The moon, our quiet companion for 4.5 billion years, is also plasma. It happened too fast to even see. Mars goes. The asteroid belt goes. Every single asteroid, every dwarf planet, every chunk of ice that has been floating out there since the solar system formed is now part of the star. Jupiter is gone next. The giant of our solar system, the planet that bullies all the other planets with its gravity, the planet that has its own swirling storm bigger than Earth, is just gas inside the star now. Its 60+ moons, including Europa with its hidden subsurface ocean, all of them, plasma. We are now 780 million miles from where the original sun used to be. The star is still expanding outward in our mental experiment. It is not done yet. Saturn comes next. Saturn orbits at about 886 million miles from the Sunday. The surface of Stephenson 2-18 sits at roughly 930 million miles. Saturn is just barely inside the new star. The famous rings, the moon Titan with its methane lakes, Enceladus with its ice geysers, all of it gone, burned, ionized. Only Uranus and Neptune survive. They orbit far enough out that they would now be circling the surface of a star instead of a Sunday. They would not survive long. The radiation pressure would strip their atmospheres in a few thousand years. Their cold blue colors would change into something hotter and angrier. The dwarf planet Pluto, way out in the Kuiper belt at about 3.7 billion miles from the Sun, would actually be okay for a while. Pluto would suddenly have a brand new sky, dominated by an enormous red disk taking up half its view. Pluto's surface temperature would spike dramatically. The frozen nitrogen and methane on its surface would evaporate. Pluto would briefly have a real atmosphere before that, too, was blown away by the stellar wind. This is the kind of object Stephenson 2-18 is. Not a star you orbit, not a star you build a civilization around. A star that, just by existing, would erase every intelligent species in any solar system unfortunate enough to have it as a sun. And here is what twists the knife. There are stars in the universe that might be even bigger. Here is a thought experiment, so absurd, it almost feels rude to ask. How long would it take a commercial jet airliner to fly around Stephenson 2-18? A modern Boeing 747 cruises at about 570 miles per hour. It can stay aloft for around 15 hours before refueling. On Earth, one full lap around the equator takes a 747 roughly 43 hours of flight time. You can cross the entire planet, every ocean, every continent, in less than 2 days. Now put that same plane around Stephenson 2-18. The circumference of this star is about 5.8 billion miles. Yes, billion, with a B. To travel that distance at 570 miles per hour, the 747 would need 1,160 years of non-stop flight, 11 centuries. The plane would have to take off during the height of the Viking Age and land in the present day, with no brakes, no fuel stops, no maintenance, no pilot changes. Of course, the plane couldn't actually do this. The surface of the star is around 3,200 Kelvin. The plane would melt before its first second of flight. Aluminum melts at less than 1,000 Kelvin. The cabin would catch fire instantly. The fuel would explode. The crew would be vaporized before they even understood what had happened. So let's upgrade. Let's send the fastest plane ever built, the X-15 rocket plane, flown in the 1960s by NASA test pilots like Neil Armstrong, hit a top speed of 4,520 miles per hour, almost 8 times faster than a commercial jet. At that speed, the trip around the star would still take about 146 years. Not better, still impossible. What about a spaceship? The fastest human-made object ever, the Parker Solar Probe, has reached speeds of about 430,000 miles per hour while diving toward our Sunday. At that absurd speed, it could circle Stephenson 2-18 in about 18 months. 18 months. To go around one star? Once? The only thing that can do this trip in any reasonable amount of time is light itself. A photon, traveling at 670 million miles per hour, makes one full lap around the star in roughly 8 hours and 40 minutes. Compare that to our Sun, where light makes the same trip in 14.5 seconds. Our Sun is a sprint. Stephenson 2-18 is an endurance event for the universe's fastest runner. This is the kind of scale astronomers wrestle with every day. Distances and sizes that mock human travel speeds. Numbers that turn the most advanced spacecraft humans have ever built into something resembling a tricycle. It also tells you something important about how stars communicate with themselves. Information inside the Sun travels at light speed, more or less. A solar flare on one side of our Sun sends a pulse of light that the other side knows about almost instantly. But on Stephenson 2-18, light takes hours to cross. The far side of the star may not know what the near side is doing for half a day. That delay matters. It is part of why these giants behave so strangely. It also means that when this star starts to die, the death itself will be a slow, staggered, multi-stage event. The kind of thing the universe rarely lets us watch. For a long time, the king of the stars was Scuti. In the early 2000s, when astronomers ranked the largest known stars in the universe, Scuti sat comfortably at the top of the list. A red supergiant in the constellation Scutum, about 9,500 light-years from Earth. Its measured radius came in around 1,700, 8 times the Sunday. Wikipedia articles science documentaries, school textbooks, every internet listicle about big stars, they all crowned UY Scuti the champion. If you had asked 10 astronomers in 2015 what the biggest known star was, 8 of them would have said UY Scuti without hesitating. Then a satellite ruined everything. The European Space Agency launched the Gaia satellite in 2013. Its job was to do something that sounds simple but is actually fiendishly hard: measure, with extreme precision, the position and distance of about 1 billion stars in our galaxy. Gaia uses a technique called parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of much more distant stars. The amount of shift tells you exactly how far away a star is. When Gaia released its second batch of data in 2018, astronomers ran the numbers on UY Scuti. The new parallax measurements told a different story than the old estimates. UY Scuti was not 9,500 light-years away. It was much closer, about 4,900 light-years. That sounds like a small change. It isn't. Distance affects every other measurement. If a star is closer than you thought, it is also less luminous, less massive, and smaller than you thought. The new calculations showed that UY Scuti was probably only about 755 solar radii. That is comparable to Antares or Betelgeuse, both of which are big but absolutely not record-breaking. UY Scuti was suddenly demoted from the top of the list to somewhere in the middle of the pack. Years of textbooks, articles, and YouTube videos became outdated overnight. The internet, of course, did not get the memo. Even today, you can find dozens of websites still claiming UY Scuti is the biggest star in the universe. They are running on old information. This is one of the harshest lessons in astronomy. The numbers we publish are estimates. Sometimes they are wildly wrong. A single new measurement can rewrite the entire ranking. UY Scuti's fall happened because a satellite did its job too well. The honest result was that we had been wrong for years. Stephenson 2-18 was already known by then, but it had been treated as an interesting outlier, not the new king. After the UY Scuti demotion, astronomers took another look at the numbers for Saint 2-18. They held up 2,150 solar radii, confirmed by independent measurements of the surrounding cluster, the dust extinction, the brightness, and the temperature. Stephenson 2-18 quietly took the crown. The question now is whether it can hold it. Other candidates are circling. WO G64 in the Large Magellanic Cloud, a galaxy that orbits our own, recently underwent a dramatic transformation that may change its ranking. New telescopes are finding stars that may rival or exceed Saint 2-18. The throne is not as stable as it looks. How do you measure something 19,000 light-years away? You cannot send a tape measure. You cannot bounce a radar signal off it and wait for the echo. The round trip would take 38,000 years. The only thing you have to work with is a faint trickle of light that has been traveling since before the agricultural revolution. Astronomers have invented a clever workaround. It is called parallax, and it is the trick that lets us measure cosmic distances at all. Hold a finger up at arm's length. Close your left eye and look at it with your right eye. Note where it appears against the background. Now switch eyes. Your finger appears to jump sideways. The closer your finger is, the bigger the jump. This is parallax. Your two eyes give you slightly different angles, and your brain uses that difference to figure out how far away things are. Astronomers do the same thing with Earth's orbit. They observe a star in January. 6 months later, in July, they observe it again. By then, Earth has moved 186 million miles to the other side of its orbit. From the star's perspective, our viewing angle has shifted. Nearby stars appear to wiggle slightly against the background of more distant stars. The amount of wiggle reveals the distance. The problem is that the wiggles are unbelievably small. We are talking about angles measured in arcseconds, which are tiny. 1 arcsecond is 1/3600th of a degree. For stars thousands of light-years away, The wiggle is only a small fraction of an arcsecond. Measuring it from the ground through a turbulent atmosphere is nearly impossible. The Gaia satellite changed everything. Sitting in space, free of atmospheric distortion, with extremely sensitive instruments, Gaia can measure parallax angles smaller than the width of a human hair held up at the distance of the moon. It is, by any honest measure, the most precise instrument for measuring the universe ever built. Gaia mapped over 1 billion stars between 2013 and 2025. It produced multiple data releases, each more accurate than the last, and every release shook up our understanding of the galaxy. Stars that had been mismeasured for decades suddenly had reliable distances. Some got closer, some got farther. Stellar luminosities, sizes, and masses were recalculated en masse. For Stephenson 2-18, the picture was actually messy. The star is so deeply embedded in dust that Gaia could not get a clean parallax measurement directly. Instead, astronomers had to measure the distance to the surrounding star cluster, Stephenson 2, and assume the star is part of it. If Saint 2-18 is genuinely a member of that cluster, its distance is around 18,900 light-years, and its size is around 2,150 solar radii. If it is not actually in the cluster, if it is a foreground or background star that just happens to look like a member, the size could be very different. This is one of the main controversies. A few astronomers have argued that Saint 2-18 might not be a true cluster member. If they are right, the size could shrink dramatically, and the star would lose its crown the way UY Scuti did. The argument is unresolved. New data keeps coming in, and somewhere out in the dust, the star pulses on, indifferent to our debates. Ask 3 astronomers how big Stephenson 2-18 is, and you will get 4 answers. The official number, 2,150 solar radii, comes from a 2012 study using the Australia Telescope Compact Array and a model called DUSTY. The team, led by researchers studying the Stephenson 2 cluster, calibrated the measurements against the cluster's distance and the dust extinction. They published their result. It became the headline figure, but not everyone is convinced. A second group of astronomers ran their own analysis using slightly different assumptions about the dust and arrived at a much smaller number. Some of their estimates put Saint 2-18 closer to 1,000 solar radii, still huge, but not record-breaking. They argued that the original team had overcorrected for dust extinction, making the star appear brighter and therefore larger than it really is. A third group went the other direction. Looking at infrared brightness measurements, they suggested the star might be even bigger, possibly close to 2,600 solar radii under some models. That number would put Saint 2-18 well past any theoretical limit and would force physicists to rewrite parts of stellar evolution theory. So which is right? Honestly, nobody knows. The reason the debate keeps going is that all of these numbers depend on assumptions you cannot test directly. How thick is the dust? Where is the star's true surface at the photosphere, or further out in the puffy atmosphere? Is the star actually in the Stephenson 2 cluster, or just nearby? How accurate are the brightness measurements, given that infrared cameras have their own quirks? Each assumption is reasonable. Each one shifts the answer. Multiply enough small uncertainties together, and you get a final number with a huge error bar. Here is what is not in dispute. Stephenson 2-18 is genuinely enormous. Even the most conservative estimates make it one of the largest red supergiants known. Even the smallest plausible size puts it bigger than Betelgeuse, the star marking Orion's shoulder, which is itself so huge it would swallow Mars if it replaced our Sunday. The argument is not whether Saint 2-18 is gigantic. The argument is whether it is the most gigantic. This is normal in astronomy. The bigger the object, the harder it is to measure precisely. Galaxies, dark matter halos, supermassive black holes, all of them come with massive uncertainty bars. We are pushing the limits of what light can tell us across thousands of light years of space. The way the question gets settled is through better instruments. The James Webb Space Telescope, which launched in 2021 and started returning data in 2022, has the sensitivity to peel back the dust shroud around Saint 2-18 and look more directly at the star's surface. Several teams are using Webb data right now to refine the measurements. Some preliminary results have come in. They mostly support the larger size, but mostly is not the same as settled. One of the strangest twists in the whole story is that even if we get a perfect measurement today, the star itself might already be different. Red supergiants pulsate. They breathe, they lose mass. The Saint 2-18 we measure now is not the same Saint 2-18 from 30 years ago. It is changing. Visibly, measurably, surprisingly fast. Stephenson 2-18 does not sit alone. It belongs to a star cluster called Stephenson 2, and that cluster is a freak of nature. Most star clusters in our galaxy are quiet, ordinary places. A few hundred stars, mostly average-sized, mostly stable. Stephenson 2 is different. It is one of the most massive young clusters in the entire Milky Way, packed with red supergiants, giant dying stars at a density nobody fully expected. When Charles Stephenson identified the cluster in 1990, he saw a tight knot of bright infrared sources. Later studies showed the cluster contains an estimated 80,000 stars. Of those, more than 24 are confirmed red supergiants. 24 in a single cluster. For comparison, the entire Milky Way contains only a few hundred known red supergiants total. Stephenson 2 has nearly 10% of all known red supergiants in the galaxy, crammed into a region a few light years across. That is not normal. That is extraordinary. The cluster sits about 18,900 light-years from Earth, near the inner edge of the Milky Way's bar, the thick cigar-shaped structure of stars and gas at our galaxy's center. This region is one of the most active star-forming zones in the entire galaxy. Massive clouds of gas collapse here at high rates, churning out enormous, short-lived stars. These big stars do not last long. A red supergiant phase lasts maybe a few 100,000 years. That is a blink in cosmic time. The fact that Stephenson 2 has so many supergiants right now, all at once, tells us the cluster itself is young, probably between 14 and 20 million years old. Old enough for its biggest stars to be near death. Young enough that they have not all exploded yet. In the next million years, this cluster will witness a stunning fireworks display. One by one, the red supergiants will die. Each will detonate in a supernova, briefly outshining the entire galaxy. The blast waves will expand outward, slamming into surrounding gas, triggering new star formation. The cluster will be reshaped. By the time the last supergiant goes, Stephenson 2 will be unrecognizable. Stephenson 2-18 is just the biggest one in the room. It is the headliner, but it is surrounded by other monsters. Stephenson 2-1, Stephenson 2-3, Stephenson 2-5, and so on. Each is a red supergiant in its own right, each potentially capable of going supernova in the relatively near future. Some of them may even be similar in size to Saint 2-18. The numbers for some neighbors are surprisingly large, though all smaller than the headliner. This is one of the reasons measuring Saint 2-18 is hard. The cluster is so dense with bright stars that distinguishing one giant from its neighbors, especially through dust, takes painstaking work. Light from one star can blend with light from another. Astronomers have to use careful image processing and high-resolution spectroscopy to separate the signals. The cluster also contains hot blue giants that have not yet evolved to the red phase. They are the next wave. In a few 100,000 years, after the current red supergiants explode, these hot stars will swell, redden, and become the new generation of giants in the cluster. It is a stellar nursery, a graveyard, and a fireworks show, all at once. Brightness, in astronomy, has a specific meaning. It is not just how bright a star looks from Earth. That depends on distance. A faint candle next to your face looks brighter than a stadium light a mile away. To compare stars fairly, astronomers measure their intrinsic luminosity, the total amount of energy a star emits per second, regardless of how far it is. Our Sun pours out about 3.8 times 10 to the 26 watts of power continuously. That number is a 3 followed by 26 zeros. To put it in human terms, the Sun produces more energy in 1 second than humanity has produced in its entire history. Stephenson 2-18 produces about 440,000 times more power than our Sunday. Take a moment with that. 440,000 suns worth of energy, gushing out continuously every second from a single object in the constellation Scutum. It is so bright that, despite being 18,900 light-years away and behind a thick wall of dust, the star is still detectable from Earth. If you put Stephenson 2-18 in our solar system at the same distance as our Sun is now, the consequences would be brutal. The Earth-facing side of the planet would receive about 440,000 times the solar radiation we currently get. Oceans would not evaporate, they would explode. The atmosphere would be blown into space within seconds. Anything organic would carbonize before it could even register the temperature change. Earth itself, the rocky planet, would melt and possibly vaporize from the outside in. This is just on the day side. The night side would not survive much longer. Within hours, the entire planet would be a glowing ball of liquid rock. Most of the energy that Stephenson 2-18 pours out is not visible light. The star is relatively cool by stellar standards, around 3,200 Kelvin. It glows mostly in red and infrared wavelengths. Hotter stars, like our Sun, peak in yellow and white. The hottest stars peak in blue and ultraviolet. St. 2-18 is a giant infrared furnace. This matters for how we detect it. Visible light cameras barely see the star. Infrared cameras see it as a blazing beacon. Astronomers using infrared sky surveys can spot it from across the galaxy, even through the dust. Because dust is mostly transparent at the wavelengths the star prefers to emit, there is a paradox here. How can a star be both incredibly luminous and incredibly cool at the same time? The answer is size. Brightness depends on two things: temperature and surface area. A small, hot star can be very bright. A huge, cool star can also be very bright, just by having a vast surface to radiate from. Stephenson 2-18 takes the second route. It is cooler than our Sun, but it has a surface area millions of times larger. The total energy output is staggering. This is also why the star is dying so quickly. It is burning through its nuclear fuel at an absurd rate. Our Sun will live for about 10 billion years total. St. 2-18 has been around for maybe 10 to 20 million years and is already in the final stages of its life. A star that bright burns out fast, and the closer to death it gets, the weirder the star becomes. There is something deeply counterintuitive about red supergiants. The biggest stars in the universe are also among the coolest. Our Sun has a surface temperature of about 5,772 Kelvin. That is hot enough to glow yellow-white. Hotter stars glow blue. The hottest stars in the universe, Wolf-Rayet stars and massive blue giants, can hit 200,000 Kelvin or more on their surfaces. They blaze with ultraviolet light so intense that getting close to them would shred your DNA before you even felt the heat. Stephenson 2-18 has a surface temperature of about 3,200 Kelvin. That is genuinely cool. A jet engine exhaust burns hotter than that. The surface of this star is roughly half as hot as our Sun's surface. Yet inside its core, fusion reactions are producing more energy than 440,000 suns combined. How is that possible? The trick is that the heat generated in the core has to travel a very long way to get to the surface. In our Sun, the journey from core to surface is about 432,000 miles. In Stephenson 2-18, that journey is 930 million miles. The energy spreads out over a vastly larger volume before it escapes. By the time it reaches the surface, it has cooled significantly. Imagine a small, intense campfire versus an enormous bonfire spread across a football field. The campfire's flames might reach a few hundred Kelvin. The spread-out bonfire produces more total heat, but each individual square foot is cooler. Stephenson 2-18 is the spread-out bonfire of the universe. Massive total output. Cool surface. The cool surface gives the star its red color. Red supergiants glow red for the same reason an electric stove burner glows red when you first turn it on. As something heats up from cold to white hot, it passes through red, orange, yellow, and white. 3200 Kelvin sits firmly in the deep red zone, a bright cherry red, not a fiery orange. Inside the star, things are very different. The core temperature is somewhere between 100 million and 1 billion Kelvin, depending on what is fusing at any given moment. At those temperatures, atomic nuclei smash into each other so violently that they fuse, releasing energy. In the final stages of a red supergiant's life, the core is fusing helium, then carbon, then oxygen, then neon, then silicon. Each new element burns hotter and faster than the last. Stephenson 2-18 is somewhere in the helium or carbon fusing stage right now. Probably. Honestly, with measurements 18,900 years out of date, we cannot be certain. The cool surface and hot core create another bizarre property. The star is convective on a massive scale. Hot gas from deep inside rises to the surface, cools, and sinks back down. These convection cells are not little eddies like the boiling water in your kettle. They are individual cells the size of solar systems. A single convection cell on Saint 2-18 might be larger than the entire orbit of the Sun's planets. This means the star's surface looks lumpy and chaotic, not smooth. It has giant rolling boils that shift over months and years. The whole surface is in constant motion. The boundary between star and space is fuzzy, always shifting, always uncertain. That fuzziness is a major problem when you are trying to measure exactly how big the star is. There is a hard physical limit on how cold a red supergiant can be while still holding itself together. It is called the Hayashi limit, named after the Japanese astrophysicist Chushiro Hayashi, who worked out the math in the 1960s. The rule is simple. If a star tries to get any cooler and any bigger than the Hayashi limit, it stops being able to support its own weight. The outer layers cannot resist gravity anymore. The star starts to fall apart. For a red supergiant of typical mass, the Hayashi limit sits around 3,000 to 3,500 Kelvin on the surface. Stephenson 2-18 sits at about 3,200 Kelvin. It is bumping right against the limit, maybe past it. This is one of the most controversial aspects of the star. If the size estimate of 2,150 solar radii is correct, then Saint 2-18 is sitting in territory where, according to standard stellar physics, it should not be stable. It should be shedding its outer layers rapidly. It should be getting smaller as we watch. Some astronomers think this is exactly what is happening. The star is in a brief, unstable phase, right at the very end of its life. It has bloated up to a record size, but it cannot maintain that size. Within a few thousand years, it will lose enough mass to shrink. Then it will go supernova. Other astronomers think the size estimate is just wrong. They argue that the star is somewhat smaller, well within the Hayashi limit, and the larger numbers come from systematic errors in how we measure the dust around it. Both camps have evidence. Both camps publish papers. The truth is somewhere in the middle, and we may not know for sure until much better instruments come online. What is clear is that red supergiants near the Hayashi limit do strange things. They pulsate violently. They eject huge amounts of mass in irregular bursts. They sometimes brighten and dim by orders of magnitude over months. Betelgeuse, the famous red supergiant in Orion, dimmed dramatically in 2019 and 2020 in a great dimming event that startled astronomers. It was probably caused by a massive ejection of dust that briefly blocked the light. Stephenson 2-18 may be doing something similar, just on a larger scale and harder to see. The convective cells on the surface play a role here. Hot gas rising from the deep interior can break through the outer atmosphere and fling material into space. When these eruptions happen, they cool and condense into dust grains, which then drift outward. Over time, this builds up a personal dust cocoon around the star. That cocoon further confuses our measurements. Here is the strange beauty of it. A star this big should not exist for very long. The Hayashi limit, mass loss rates, and core fusion timescales all point to a very short life expectancy at this stage. Saint 2-18 has maybe a few 100,000 years left before it goes supernova, probably much less. In cosmic terms, that is the equivalent of meeting someone who is 100 years old and learning they have only weeks left. We caught this star at the very last possible moment, and what comes after the supernova will be even stranger. Surrounding Stephenson 2-18 is a personal cloud of dust, not the dust between us and the star, that is interstellar dust, contributed by the broader galaxy. This is local dust. Dust that the star itself has been pumping out into space for thousands of years. Red supergiants are dust factories. As they reach the end of their lives, they shed their outer layers in slow, continuous streams of material. The gas leaving the surface cools as it expands. When it gets cold enough, atoms start sticking together. Carbon atoms bond into chains. Silicon atoms form into tiny crystals. Eventually, microscopic grains of solid material condense out of the gas soot and silicate dust. These grains drift outward, pushed by radiation pressure from the star itself. Over time, the dust builds up into a shell around the star. For Saint 2-18, this dust shell is enormous. Light leaving the star's surface has to fight through this shell before it can begin its journey across the galaxy. Some of the light gets absorbed by the dust, then re-emitted at longer wavelengths. The dust acts like a frosted lampshade, diffusing the bright glow of the star inside. This creates a strange situation. When astronomers look at Stephenson 2-18, they cannot easily tell whether the light they see is coming from the star directly or from the dust shell around it. Both glow. Both contribute to the total brightness. Disentangling the two is one of the major challenges in measuring the star. Researchers use computer models, like the Dusty code, to simulate how light passes through the dust shell. They feed in measurements at different wavelengths, visible, near-infrared, mid-infrared. And the model tries to figure out how much dust there is, how it is distributed, and what the underlying star looks like. It is sophisticated, but it requires assumptions. Different assumptions give different answers. The dust shell also tells us something important about the star's recent history. By measuring the size and density of the shell, astronomers can estimate how much mass the star has been losing per year. For Saint 2-18, the answer is staggering. Roughly 1/10,000th of a solar mass per year is being shed. Over 100,000 years, that adds up to a full sun's worth of material drifting away. This is mass that came from inside the star. Hydrogen, helium, carbon, oxygen, the elements that nuclear fusion built up over millions of years, slowly being returned to the galaxy. It will eventually mix with the interstellar medium. Some of it may end up in new stars. Some of it may end up in new planets. Some of it may end up in living organisms billions of years from now. This is how the universe recycles. The atoms in your body came from stars that died billions of years ago. The atoms in Stephenson 2-18 eventually will become part of something new. Maybe a planet, maybe an organism, maybe a creature that wonders about the stars the way we do. The dust shell is a graveyard and a nursery in one, and the rate at which Saint 2-18 is shedding material is accelerating, getting more violent as the star nears its final breath. The next eruption could happen at any time. Stephenson 2-18 is hemorrhaging mass. Every year, it loses about 1/10,000th of a solar mass to the wind streaming off its surface. That number sounds small. It is not. Spread over a century, It adds up to almost one full solar mass. Over 100,000 years, the star will have lost 10 suns worth of material into space. For a star whose total mass might be around 40 suns, that is a huge fraction of itself disappearing into the void. The mechanism is called stellar wind. Our own sun has a stellar wind too, but it is gentle. The sun loses about 1/1,000,000th of a solar mass per year. Saint 2-18 loses something like 100 million times more material than the sun per second. It is a hurricane compared to the sun's gentle breeze. The wind is not steady, it comes in pulses and gusts. Sometimes the star ejects huge globs of material in a single dramatic event. Sometimes it loses mass slowly and gradually for years before erupting again. The exact pattern is messy, irregular, and not fully understood. Astronomers track the changes by watching the dust shell around the star expand over time. What drives this wind? Two main forces work together. The first is radiation pressure. Light leaving the star pushes on dust, grains, and gas atoms. With 440,000 suns of luminosity blasting outward, that push is enormous. Anything not firmly held by gravity gets shoved outward into space. The second force is convection. Hot gas rising from deep inside the star reaches the surface with enough energy to escape, like steam blowing off a pot of boiling water. In a normal red supergiant, these two forces work together in a relatively orderly way. In Stephenson 2-18, they may be pushed to their absolute limits. The star is so big and so close to its physical size limit that any small disturbance can cause a major eruption, a particularly large convection cell pushing through the surface, a pulsation that briefly inflates the star, a change in the magnetic field. Any of these can trigger a massive ejection of material. When it happens, the ejected material races outward at speeds of around 40,000 miles per hour. That sounds fast. By stellar standards, it is actually slow. Wind from blue giants can hit 100 times that speed. But Saint 2-18's wind makes up for its slowness with sheer volume. It is moving more material per unit time than almost any other star known. This mass loss is not just a curiosity. It is part of how the star kills itself. As the outer layers blow away, the star's gravity weakens. The remaining material is less compressed. The internal pressure changes. The fusion reactions in the core have to adjust to the new structure. Eventually, the star becomes unstable enough that the core collapses, triggering a supernova. Without this mass loss, supernovae would look very different. The ejected material from the wind interacts with the supernova's blast wave, creating spectacular shock structures and complex geometries. The wind is essentially preparing the stage for the explosion. For Saint 2-18, the wind is a slow countdown. Each ton of material lost brings the explosion closer. Each pulse brings the moment of detonation a little nearer. The star is unwinding itself in real time. Astronomers cannot say exactly when the end will come, but they can say what they expect to see. How do you weigh something you cannot touch, cannot visit, and cannot even see clearly through a wall of dust? This is the puzzle astronomers face with Stephenson 2-18. Mass is one of the most important properties of a star. It determines how long the star lives, how brightly it shines, what kind of supernova it will become, and what it leaves behind when it dies. Get the mass wrong, and you get everything else wrong too. For most stars, the easiest way to measure mass is to find a companion. If two stars orbit each other, you can watch their dance, time the orbits, and use Newton's laws of gravity to calculate how heavy they are. The bigger the star, the faster the dance. The math is straightforward when you have a partner to work with. Stephenson 2-18 has no known companion. It appears to be a single, isolated, red supergiant, so that method is off the table. Astronomers fall back on a less direct technique. They compare the star to theoretical models. They take the measured brightness, the surface temperature, the size, and the chemical composition. Then they ask their computer simulations a question: what kind of star, at what stage of life, would look exactly like this? The simulation spit out an answer. Stephenson 2-18 has an initial mass somewhere between 20 and 40 times the Sunday. It probably started life closer to the upper end of that range. By now, after millions of years of fusion and a couple 100,000 years of aggressive mass loss, it has shed a noticeable fraction. The current mass is probably around 15 to 20 suns. Yes, you read that right. A star with a volume 10 billion times bigger than the Sun has a mass only 15 to 20 times bigger. Its average density is unbelievably low. If you had a piece of the star's outer atmosphere in your hand, it would feel lighter than the air in your room. Most of Saint 2-18 is closer to a vacuum than to anything solid. This low density is a feature of all bloated red supergiants. As they age and swell, their material spreads thin. The core stays dense and hot, fusing elements at extreme rates. But the outer layers, where most of the volume lives, are barely there. They are held in place only by gravity and the constant flow of energy from below. This is also why mass loss is so easy for these stars. There is not much holding the outer layers in place. A tiny push, and material drifts away. A bigger push, and material gets ejected entirely. The radiation pressure does most of the heavy lifting. The mass also determines what happens at the end. A star that started with 20 solar masses goes one direction. A star that started with 40 solar masses goes another. The first leaves behind a neutron star. The second probably leaves behind a black hole. Both are dramatic. They are very different. Stephenson 2-18 sits right at the boundary between these two outcomes. Depending on its exact starting mass and how much material it has lost, it could end up as either astronomers genuinely cannot predict which fate is waiting. The uncertainty is frustrating. It is also a sign of how much we still have to learn about the most massive stars in the universe. Try to define the surface of a star. For our Sun, this is reasonable. The Sun has a relatively sharp boundary called the photosphere, where the gas becomes thin enough that light can escape directly into space. Above the photosphere, the atmosphere thins out into the corona. Below it, the gas is too dense for light to travel freely. The photosphere is the visible surface, the place where the Sun stops being opaque and starts being transparent. For Stephenson 2-18, this definition breaks down. The star is so large and so puffed up that there is no clean boundary anywhere. The gas density decreases gradually over an enormous range. There is no single layer where everything suddenly becomes transparent. Instead, there is a fuzzy, smoky transition zone that may stretch for tens of millions of miles. Inside this zone, light is partially absorbed and partially scattered. Some photons escape directly. Some get bounced around for ages before finally making it out. So when astronomers say Stephenson 2-18 has a radius of 2,150 solar radii, they have to specify what they mean by radius. Usually, they pick a specific definition, like the Rosseland radius, the place where the average optical depth equals 2/3. That is a technical way of saying the place where most of the light gets out. It is a useful definition. It is also somewhat arbitrary. A different definition gives a different number. Some astronomers measure the size based on where dust starts to form in the outer atmosphere. That gives an even larger radius. Others measure it based on infrared emission, which can include light coming from the dust shell as well as from the star itself. That can also give a different answer. This is why size estimates for red supergiants always come with error bars. The star does not have a single, well-defined edge. It has a fuzzy outer region that grades smoothly into the surrounding wind. Imagine trying to measure the size of a cloud. Where does the cloud end? At the visible edge, where you can clearly see white wisps. At the slightly hazy zone just outside that. At the invisible boundary where humidity starts to drop back to normal levels. Each definition gives a different number. None of them is wrong. They are just measuring different things. Stephenson 2-18 is the same. It is a giant glowing cloud of plasma, and the edge is where you decide to put it. This fuzziness has consequences. The star's mass loss happens in this fuzzy zone, where gas is barely held back by gravity. The dust shell forms here. The convection cells can break through here. Pulsations in the deeper layers ripple outward and shake this region. It also means the star's size is genuinely changing all the time. Pulsations cause the outer layers to expand and contract by significant amounts over months and years. Eruptions cause sudden inflations. Mass loss causes gradual changes. The Saint 2-18 of today is not exactly the same size as the Saint 2-18 of a decade ago, even if the change is small in percentage terms. The frustrating part is that, with current technology, we cannot resolve any of this in real time. The star is too far away, even with our best telescopes, to see its surface as anything more than a glowing blob. That is starting to change. Stephenson 2-18 is not standing still. Like most red supergiants, it pulsates. The whole star expands a little, then contracts a little, then expands again, in a slow, rhythmic cycle. The pulsations are driven by instabilities in the outer layers, radiation pressure pushing outward, gravity pulling inward, ionization changes, affecting how light interacts with gas. The result is a heartbeat that takes years to complete. For Saint 2-18, the pulsation period is probably around several hundred to 1,000 days. The exact number is hard to pin down because the star is faint in visible light and the dust complicates measurements. But astronomers have detected variations in its brightness consistent with this kind of slow oscillation. When the star expands, its surface area increases and the temperature drops slightly. The total brightness changes a little. When it contracts, temperature goes up and the area shrinks. These competing effects mean the brightness change is not always huge, but it is detectable with sensitive instruments. These pulsations are not just random wobbles. They tell astronomers important things about the star's internal structure. The period of the pulsation depends on the star's mass and radius. Bigger, less massive stars pulsate more slowly. Smaller, denser stars pulsate faster. By measuring the period, you can constrain the star's properties and check your other measurements. For Saint 2-18, the pulsation period is consistent with a very large, very low-density star, which is what every other line of evidence suggests. The pulsations agree with the size estimates. There is something poetic about a star this big, breathing this slowly. Each cycle takes about as long as the entire history of human spaceflight from Sputnik to now. The star inhales. The star exhales. Years pass. The star inhales again. The pulsations also affect the mass loss. When the star expands, it briefly cools and weakens its grip on the outer layers. Material can escape more easily. When it contracts, it compresses the surrounding gas and can trigger dust formation at certain distances. The slow rhythm of breathing translates into a pulsing wind. In some red supergiants, the pulsations become unstable. The amplitude grows over time. Each cycle is bigger than the last. Eventually, the star starts ejecting material in massive bursts rather than steady winds. This is sometimes called an eruption. Famous red supergiants like VY Canis Majoris are known for these dramatic events. Stephenson 2-18 may be on a similar path. We do not know for sure. Its current mass loss rate is high, but consistent with a steady wind rather than an eruption. That could change in the next 1,000 years, or the next year. The line between stable mass loss and explosive ejection is thin and unpredictable. If an eruption happens, it would be visible from Earth. The star would brighten dramatically, possibly by a factor of 10 or more. The dust shell would expand suddenly. New dust would form rapidly as the ejected material cooled. We might see a once-in-a-civilization event play out in real time, but the slow heartbeat continues for now. The star breathes, the galaxy waits, astronomers watch, and every breath brings the final moment closer. Stephenson 2-18 is, in cosmic terms, a child. The star formed somewhere between 10 and 20 million years ago. Compare that to our Sun, which is 4.6 billion years old, or to the universe itself, which is 13.8 billion years old. Saint 2-18 has existed for a fraction of 1% of the universe's lifetime, yet it is already dying. This is the brutal trade-off of being a massive star. The bigger you are when you form, the brighter you burn, and the faster you go through your fuel. Our Sun will live for about 10 billion years total because it burns hydrogen slowly and steadily. A star like Saint 2-18 burns hydrogen so fast that the entire main sequence phase, the long, stable middle of stellar life, lasted only a few million years. Then the star ran out of hydrogen in its core and started fusing heavier elements. Each new fuel runs out faster than the last. Hydrogen fusion lasts millions of years. Helium fusion lasts maybe a few 100,000. Carbon fusion lasts a few 100 years. Oxygen fusion, less than a year. Silicon fusion, just days. Saint 2-18 is somewhere in this ladder right now, probably fusing helium, possibly already onto carbon. Each step shrinks its remaining lifespan dramatically. By the time it gets to silicon, the star will have hours left, not years. The reason this happens is energy efficiency. Hydrogen fusion releases huge amounts of energy per reaction. Each subsequent fusion stage releases less. By the time you get to silicon, you are getting almost no energy out per reaction. The star has to fuse more material just to keep itself from collapsing under its own gravity. The final stages of life are a desperate, accelerating race. This is why massive stars like Saint 2-18 are so rare. They do not last long enough to accumulate. For every red supergiant in the galaxy, there are millions of small, ordinary stars like our Sun that have been quietly burning for billions of years. The big ones come and go in a flash. They are always new. There is a strange dignity in this. Stephenson 2-18 will live a short, intense, luminous life. It will produce more energy in its few million years than our Sun will produce in its 10 billion. It will create heavy elements, oxygen, silicon, sulfur, iron that did not exist before. It will scatter those elements across the galaxy when it dies. Some of them will end up in new stars and new planets. The atoms in your blood, the calcium in your bones, the oxygen you breathe, all of it came from stars like Saint 2-18, or rather, from stars that died billions of years ago in similar explosions. We are descendants of dying giants. We are made of their guts. The lifetime of a star this big is a paradox. By human standards, it is unimaginably long. By cosmic standards, it is brief. By the standards of the elements that make up your body, it is a critical engine of creation. And right now, at this very moment in galactic history, Saint 2-18 is preparing for its final act. The countdown is ticking down. The fuel is running out. The core is heating up. The end is closer than you think. How much time does Stephenson 2-18 have left? This is the question every astronomer who studies it eventually asks. The honest answer is that we do not know precisely. Stellar evolution at this stage is brutally hard to predict. The star could explode tomorrow. It could explode in 10,000 years. It could explode in 100,000 years. The error bars are massive. Here is what we can say. The star is in the final phase of its life. The hydrogen in its core is gone. It is fusing heavier elements now. Each new fuel buys the star a shorter and shorter amount of time. The total remaining lifespan, in cosmic terms, is short. Models suggest a few thousand to a few 100,000 years. That is the rough window. After that, the core will run out of fuel that can release energy through fusion. At that point, the core collapses and the star detonates as a core collapse supernova. A few thousand years sounds long. To you, it is. To the universe, it is the blink of an eye. If Saint 2-18 formed 20 million years ago, then a few thousand years is less than 0.1% of its total life. It would be the equivalent of an 80-year-old human having a few hours left to live. There is also a chance, though astronomers consider it unlikely, that the star has already exploded. Remember, we are seeing light that left it 18,900 years ago. Anything that has happened to the star in the last 19 millennia is invisible to us. It might be a supernova remnant right now, and we just have not gotten the news yet. If it has already gone off, the light from the explosion is on its way. It is currently somewhere between Saint 2-18 and Earth, racing through the galaxy at light speed, getting closer every second. We will not know about it until it arrives. There is no way to find out earlier. The universe simply does not let information travel faster than light. This is a deeply weird situation to sit with. Every time you point a telescope at a distant star, you are looking at a possibly stale image. The star you see may not exist anymore. The reverse is also true. Stars that look unchanged might be in the middle of changing dramatically right now. Astronomers have to live with this delay. It is one of the fundamental limitations of studying objects that are far away. It also means that the universe is, in a sense, much more dramatic than what we observe. There are probably hundreds of supernovae happening across the universe right now, but their light has not reached us yet. We only see the explosions whose light has already arrived. For Saint 2-18 specifically, the most likely scenario is that it is still alive, still pulsating, still bleeding mass into space. The end is approaching, but it is probably not here yet. The star is in its final phase, but final phases can last a long time on human timescales. When the moment comes, it will be one of the most violent events the galaxy can produce. The energy released in the first second will rival the energy our sun produces in its entire lifetime. What kind of explosion will it be? That is its own debate. Supernovae are not all the same. There are several main types, and the type a star produces depends on its mass, its composition, and the exact conditions at the moment of collapse. Each type has its own signature, its own brightness, its own duration, and its own remnant left behind. For Stephenson 2-18, astronomers expect a Type 2p supernova. The 2 means the star still has a hydrogen-rich outer layer when it explodes. The P stands for plateau, because these supernovae have a brightness curve that levels off for a few months before fading. They are common. Most red supergiants in the galaxy that explode produce this type. The mechanism is core collapse. After the star runs out of fuel that can release energy, the core can no longer support itself against gravity. In a fraction of a second, the core collapses inward. Outer layers fall onto the collapsed core, bounce off, and rebound outward in a massive shockwave. The shockwave tears through the star, blowing it apart. The light output is staggering. A typical Type 2p supernova reaches about 1 billion times the brightness of our Sun at peak. Stephenson 2-18, given its size and probable mass, would land somewhere in this range, possibly toward the brighter end. The star already shines 440,000 times brighter than the Sunday. When it explodes, its peak brightness will jump by a factor of around 2,000 or more. For a few weeks, this single dying star would outshine the entire Milky Way galaxy in raw output. From 18,900 light-years away, it would be visible from Earth without a telescope, possibly visible during the day. It would dominate the night sky for months. The visible explosion is just the start. A core collapse supernova also releases a flood of neutrinos, tiny, nearly massless particles that interact almost not at all with normal matter. About 99% of the energy in a supernova goes into neutrinos. They escape the star instantly. For Saint 2-18, the neutrinos would arrive at Earth a few hours before the visible light, because the visible light has to fight its way out through the collapsing material. If the explosion happened tomorrow, our neutrino detectors on Earth would catch the burst before any optical telescope saw the flash. We would have a few hours of warning to point everything we had at the right spot in the sky. The supernova would also produce huge amounts of heavy elements. In the explosion, atoms are smashed together at enormous energies, fusing into elements heavier than iron, gold, platinum, Uranium, the heavy stuff in the universe, gets created during these final moments. A single Saint 2-18 supernova would produce more gold than humanity has ever mined. That gold drifts outward into space, eventually mixing with interstellar gas, eventually being incorporated into new stars and planets. The wedding ring on someone's finger billions of years from now might contain atoms forged in the death of Saint 2-18. This is the standard picture. But there are some weird possibilities too. Some massive stars do not produce a normal supernova. They do something stranger. Not all massive stars explode visibly when they die. Some, according to recent theories, simply collapse. The core falls in. The outer layers do not bounce. Instead, they get swallowed. The star does not detonate. It just disappears. From the outside, it looks like a star that was there one day and is gone the next, with no spectacular fireworks in between. This is called a failed supernova. For a long time, it was just a theoretical possibility. Then, in 2015, astronomers studying a particular red supergiant in a distant galaxy reported something striking. The star had vanished without an explosion. Where there was once a bright supergiant, there was now a faint infrared glow that could be a black hole accreting material. The star, called N6300-22, may have failed. If failed supernovae are real, they are common. Astronomers estimate that maybe 20 to 50% of massive stars die this way, instead of producing the normal bright explosions. This is one possible explanation for why we see fewer supernovae than we would expect, given how many massive stars are out there. Could Stephenson 2-18 die this way? Possibly. The exact threshold for a failed supernova is debated, but it generally happens to the most massive stars, those above about 30 solar masses at the time of collapse. Saint 2-18 probably falls into this category, though it is on the lower edge after years of mass loss. If Saint 2-18 failed instead of exploding, the consequences would be very different. Instead of a brilliant flash visible across the galaxy, there would be a quiet dimming. The star would simply fade away over weeks or months. A telescope pointed at the right spot would see a slow disappearance, not a dramatic blast. The remnant would be a black hole, a relatively quiet one, maybe 20 solar masses or so. Most of the original star's mass would fall into the black hole rather than getting blasted into space. The galaxy would lose a major source of heavy elements. The neutron star that might have been formed would never exist. Astronomers would still detect something. The neutrino burst from the collapse would still happen. That part is automatic when a stellar core gives way. We would see the neutrinos and know that something massive had died. But there would be no optical fireworks to follow up with. The star would simply be missing the next time we looked. This is a relatively new idea in astronomy. The first confirmed candidates for failed supernovae have only been identified in the last decade. We do not yet have a clean catalogue of them. We do not know exactly what conditions cause a star to fail rather than explode. For Saint 2-18, the most likely outcome is still a normal Type 2p supernova. But the failed scenario remains on the table. It is a possibility that astronomers consider. This adds another layer of uncertainty to the prediction. Even if we knew exactly when the star would die, we cannot say for sure how it would die. The universe has options. The universe sometimes picks the strange option. A black hole in our galaxy, born quietly, with no flash to mark its arrival, is one of the more haunting ways a star can end. There is one more possibility, and it is the wildest of them all. Stephenson 2-18 could produce a gamma-ray burst. Gamma-ray bursts are the most energetic explosions in the universe. In a typical gamma-ray burst, more energy is released in a few seconds than our sun will release in its entire lifetime. The burst comes out as a tightly focused beam of gamma rays, the most energetic form of light. If you happen to be on the receiving end of that beam, you get a face full of cosmic radiation that no atmosphere can fully block. Most gamma-ray bursts come from very specific types of dying stars. They require a massive star, rapid rotation, and the right magnetic field configuration. When the core collapses, instead of producing a roughly spherical supernova, the energy gets channeled into two narrow jets, shooting out the rotation axis. The jets punch through the star at relativistic speeds and produce the gamma-ray burst when they hit the surrounding gas. Could Saint 2-18 produce one? Probably not. Most red supergiants do not. They tend to lose their outer envelopes and spin down before they collapse. Gamma-ray bursts come more often from a different type of dying star, Wolf-Rayet stars, which are very hot, very massive, and have already shed their hydrogen envelopes. Saint 2-18 still has its hydrogen envelope. That makes a gamma-ray burst less likely. But less likely is not impossible. If the star happens to be rotating fast enough, and if its magnetic field is right, the collapse could still produce a jet. The jet would not be perfectly aligned with Earth. Gamma-ray bursts are narrow beams, and the chance of any given burst pointing at us is small. But if it did point our way, we would notice. A gamma-ray burst from 18,900 light-years would be a serious event. Earth's atmosphere would absorb most of the radiation, but the upper atmosphere would be hammered. Ozone layer damage, increased ultraviolet exposure on the surface, radio blackouts, possibly long-term effects on climate. Some scientists have speculated that ancient mass extinctions may have been triggered by nearby gamma-ray bursts, though this remains unproven. For Saint 2-18 specifically, the orientation matters. We would need the rotation axis of the star to be pointing roughly at Earth for a burst to hit us. Astronomers do not currently have a good measurement of the star's rotation axis. It is one of the things we cannot easily determine through the dust. The good news is that even if Saint 2-18 does produce a gamma-ray burst, it is not in the most dangerous distance range. The truly catastrophic effects would require a burst much closer within a few thousand light-years. At 19,000 light-years, the effects would be measurable but not civilization-ending. The galaxy probably produces gamma-ray bursts every few 100,000 to a few million years. We have not seen one in the Milky Way during recorded human history. The universe has been kind to us. Statistically, our luck will eventually run out. Whether Saint 2-18 will be the next one is unknown. What is certain is that whatever explosion it produces, the shock wave that follows will travel for a long time and reshape its corner of the galaxy. When Stephenson 2-18 explodes, the energy released will not stay put. The supernova will eject roughly 10 solar masses of material at speeds of around 22 million miles per hour. That ejector carries enormous kinetic energy, about 10 to the 44th joules in total. To put that in perspective, the Sun produces 10 to the 33rd joules per second. The supernova releases 10 million billion times more energy in one event than the Sun produces in a single second. This energy expands outward as a shockwave. At first, the shockwave is dense, hot, and moving at nearly light speed. As it pushes through the surrounding gas, it slows down. Material from the star plows into the surrounding interstellar medium and creates a turbulent boundary layer. Over thousands of years, the shockwave continues to expand, sweeping up more and more gas, growing into an enormous bubble. The remnant of the supernova will eventually become a structure called a supernova remnant. We can see many examples of these in our galaxy already. The Crab Nebula is a famous one, the leftover of a supernova that humans observed in the year 1054. Cassiopeia A is another, from an explosion around 400 years ago. These remnants grow for tens of thousands of years before finally fading into the general background of the galaxy. For Saint 2-18, the remnant will eventually grow to a diameter of dozens of light-years. The Stephenson 2 cluster, where the star currently lives, will be reshaped by the explosion. Other stars in the cluster will have their atmospheres stripped, their orbits perturbed, their environments enriched with heavy elements from the blast. The shockwave will trigger new star formation. As it slams into nearby molecular clouds, the compression can collapse pockets of gas into new protostars. The death of one giant becomes the birth of dozens of smaller stars. This is how galaxies maintain themselves over billions of years. Death is followed by birth, in a continuous cycle. The shockwave also produces high-energy particles. Cosmic rays, protons, and atomic nuclei, traveling at near-light speeds, get accelerated by the shock fronts in supernova remnants. These cosmic rays then race throughout the galaxy. Some of them hit Earth's atmosphere and create the cascades of secondary particles that physicists detect with cosmic ray observatories. A noticeable fraction of the cosmic rays we currently measure come from supernovae that exploded thousands or millions of years ago. Saint 2-18 will contribute its own batch of cosmic rays after it goes. Some of those particles will travel for tens of thousands of years before eventually slamming into Earth. People living far in the future, if humanity survives that long, will measure the cosmic rays from this specific supernova and trace them back to a remnant in scutum. The energy of the explosion also enriches the galaxy's chemistry. Heavy elements created in the final moments of the star's life and during the explosion itself get scattered into space. They mix with the interstellar gas. Eventually, that enriched gas collapses into new stars and planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of these elements were originally forged in supernovae, like the one Saint 2-18 is preparing to produce. Death, in stellar terms, is generosity. The star gives back what it built. How worried should you be about Stephenson 2-18 exploding? Honestly, not very. The star is far enough away that even a worst-case supernova would not directly threaten Earth. The kill zone for a typical supernova, the distance at which it would seriously damage our biosphere, is around 50 light-years. Saint 2-18 sits at 18,900 light-years. We are roughly 380 times farther away than the danger threshold. That distance buffer matters. Even if the star produced a brilliant supernova, or even a gamma-ray burst aimed at us, the effects on Earth would be modest. We might see a new bright star in the sky. We might detect a slight increase in ultraviolet radiation. We might pick up an unusual neutrino burst. None of these would be life-threatening on a planetary scale. For comparison, Betelgeuse, the red supergiant in Orion, sits about 642 light-years from Earth. It is also a candidate to go supernova in the cosmically near future. When it explodes, it will be a much more dramatic event from our perspective. It will outshine the full moon for weeks. It will be visible during the day. It will be one of the most spectacular astronomical events in human history. But Betelgeuse is also far enough away to be safe. 642 light-years is well outside the danger zone. For a supernova to actually threaten life on Earth, it would need to happen within about 30 light-years. There are no stars within that range that are likely to go supernova in the near future. The closest candidates are much farther out. The galaxy has, by random chance, placed us in a relatively quiet neighborhood. This is not a permanent guarantee. Over millions of years, our solar system orbits the center of the galaxy and passes through different regions. We might pass close to a future supernova. Astronomers have speculated that some past mass extinctions on Earth could have been triggered by nearby stellar deaths. The Ordovician extinction, around 440 million years ago, has been suggested as a possible candidate for a gamma-ray burst trigger. The evidence is weak but not zero. For now, we are in a safe spot. Stephenson 2-18, far across the galactic plane, in the dust-shrouded inner Milky Way, poses no real threat to anyone. When it explodes, we will see it as a new bright star, briefly visible to the naked eye, then fading over months and years. It will be an astronomical spectacle, not a disaster. This is, in fact, one of the things astronomers find most interesting about Saint 2-18. It is far enough that we can study it from a safe distance, but close enough that we can study it in detail. It is in our galaxy. We can use our best telescopes to peer at it. We can measure its properties with care. We can watch its evolution, and we can model what its eventual death will look like. knowing that we will have a front row seat for the show without being in any danger. Cosmic distances are usually our enemies, blocking us from understanding what is out there. In this case, the distance is exactly right. Saint 2-18 is the perfect specimen. When it explodes, every astronomer alive will be watching. Let's imagine the moment. It is some night, decades or centuries from now. People look up at the sky and notice something new. A bright star appears in the constellation Scutum, in a region that previously held only faint stars and dust lanes. At first, the new star is a faint pinprick, then it brightens rapidly. Within hours, it is one of the brightest stars in the sky. Within days, it is brighter than Venus. Within a few weeks, it is the brightest object in the night sky after the moon. This is what Stephenson 2-18's supernova will look like from Earth. A typical Type 2P supernova at 18,900 light-years would reach a peak apparent magnitude of around -5 to -6. That is bright. For reference, Venus at its brightest is about -4.7. The full moon is about -13. So the supernova would be brighter than Venus, but significantly dimmer than the moon. It would be easily visible during twilight. It might even be visible during daytime if you knew where to look and the sky was clear. The brightness would last for weeks to months. Type 2P supernovae have a characteristic plateau in their light curve, lasting around 100 days, where the brightness stays roughly constant before fading. After the plateau, the supernova would gradually dim over the next few years until it became invisible to the naked eye again. Even after the visible explosion fades, the remnant would continue to be observable with telescopes. The expanding bubble of debris would be one of the most studied objects in the galaxy for centuries afterward. Every major observatory would point its instruments at it. New telescopes would be built specifically to study it. It would become a textbook example for generations of astronomy students. Modern astronomy has never witnessed a galactic supernova. The last visible supernova in the Milky Way that humans clearly recorded was Kepler's supernova in 1604. That was over 400 years ago. We have studied many supernovae in other galaxies, but never one in our own galaxy with modern instruments. Saint 2-18 could be the one. If it is, the scientific impact would be enormous. We would learn things about supernovae that we cannot learn from distant ones. Detailed neutrino measurements, real-time observation of the shockwave breaking out, tracking the formation of heavy elements, studying the remnant from day one. These are scientific dreams that have been waiting for a nearby supernova to come true. Every astronomer alive when it happens will remember exactly where they were when the news broke. It will be a generation-defining event, the kind of thing that gets passed down for centuries afterward. Of course, it might not happen in our lifetimes. The star could last another 50,000 years. Most likely, none of us will be around to see it. But there is also a real chance, if we are lucky, that it could happen tomorrow or last week. Remember, the light from the explosion has to travel 18,900 years to reach us. The star may have already gone. We just have not gotten the news yet. The sky might be about to change. We talked about failed supernovae briefly. They deserve more attention because they may be more common than anyone realized, and they raise an unsettling possibility for Stephenson 2-18. In recent years, astronomers have been systematically searching for stars that disappear without exploding. The technique is straightforward. Take photographs of nearby galaxies decade after decade. Compare them. Look for stars that were there in old images but are gone in new ones. If a star disappears without producing a supernova, it has probably failed. The results have been striking. A handful of clear, failed supernova candidates have been identified. Stars that vanished quietly. No flash, no remnant, just an empty spot where a giant used to be. The most studied case so far is N6300-22, a red supergiant in the galaxy NGC 6946. Located about 22 million light-years from Earth. Astronomers had been monitoring it. It went through a brief brightening event in 2009, then steadily faded. By 2015, it was completely gone in optical light. Only a faint infrared signature remained, possibly the glow of material falling into a newly formed black hole. The star did not explode. It just collapsed. The matter that should have been blasted into space was swallowed by the black hole instead. If Stephenson 2-18 does this, here is what it would look like from Earth. Over a few years, the star would gradually fade. The dust shell would persist for a while, but the underlying star would go dark. Then the dust shell would slowly disperse, and the spot would become a faint, persistent infrared source, the new black hole accreting the last bits of material around it. There would be no fireworks, no bright new star in the sky, no visible event for amateur astronomers to witness. The death would be invisible to anyone not specifically watching with sensitive instruments. This is one of the more unsettling possibilities. The galaxy could lose its largest known star quietly, with no public spectacle. The black hole left behind would be one of the more massive stellar mass black holes in our galaxy. It would be detected eventually, through gravitational effects on nearby objects, or through accretion glow if it captures any passing material. But for most people, the disappearance would be unnoticeable. The frequency of failed supernovae has implications beyond just St. 2-18. If 20 to 50% of massive stars die quietly, then the universe contains many more black holes than we previously thought. Most of these black holes would be invisible, quiet, isolated, not accreting anything. They would just be dark masses, drifting through interstellar space. Some astronomers think the failed supernova mechanism may explain why we see fewer supernovae in our galaxy than expected. Most of the giants that should be exploding are simply collapsing instead. The fireworks budget of the galaxy has been overestimated. For Stephenson 2-18, the most likely outcome is still a normal supernova. Its mass is right at the boundary, but probably not high enough to fail. Still, the possibility exists. We will not know for certain until we watch it die. And we will not watch it die for a long time. Stephenson 2-18 is the largest known star, but known is doing a lot of work in that sentence. The galaxy is vast. Our view of it is heavily biased by what we can actually see. We see best through clean lines of sight, away from dense dust lanes. We see best in the directions where surveys have been run. We see best in wavelengths that our telescopes are sensitive to. There are huge regions of our galaxy where we have only limited information. The center of the galaxy, in particular, is shrouded in dust so thick that even infrared barely makes it through. Could there be larger stars hidden in those regions? Almost certainly, yes. Astronomers have estimated that there should be hundreds of red supergiants in the inner Milky Way that we have never directly observed. They are buried behind so much dust that even our best infrared instruments struggle. Some of them may be smaller than St. 2-18. Some may be comparable. Some may be larger. The James Webb Space Telescope, launched in 2021, has begun to chip away at this problem. Its enormous mirror and ultra-sensitive infrared instruments can see through dust that Hubble could not. Webb has been peering into the inner galaxy and other dust-rich regions, and it is starting to reveal stars that were previously hidden. So far, Webb has not announced any clear competitors to St. 2-18, but the survey is ongoing. New massive stars are being identified regularly. Some of them have impressive sizes. None has clearly beaten St. 2-18, but the data is preliminary. Outside our galaxy, the picture is harder. We can only see the brightest extragalactic stars individually. Most stars in other galaxies blend into a general glow. The brightest red supergiants we can resolve in nearby galaxies, like Andromeda or the Magellanic Clouds, tend to be similar in size to the largest stars we know in our own galaxy. WO G64 in the Large Magellanic Cloud is one example. It used to be considered a serious contender. Recent observations show it has transformed from a red supergiant into a yellow hypergiant. It is shrinking and heating up as it approaches its final stage. In more distant galaxies, we cannot resolve individual stars at all. Their identities are lost in the blur of starlight. There could be enormous stars in those galaxies, but we cannot see them as individuals. This is a frustrating limitation. The largest known star is an artifact of our observational reach. The actual largest star in the universe is probably bigger, probably much bigger. We just cannot see it. This is part of why astronomy is humbling. Our catalogues are incomplete. Our knowledge is biased. The universe is mostly invisible to us, hidden behind distance, dust, and the limits of light. Every new telescope reveals new wonders that previous generations could not have known about. Stephenson 2-18 is the largest star we have managed to find so far. The next generation of telescopes will probably find something bigger, and the generation after that will probably find something bigger still. The throne is always temporary. The next pretender is always emerging from the dust. The James Webb Space Telescope changed astronomy. Launched on Christmas Day in 2021, Webb began returning science data in mid-2022. Its primary mirror is 21 feet across, more than 2.5 times the size of the Hubble Space Telescope's mirror. Its instruments are exquisitely sensitive in infrared wavelengths. It is the most powerful space telescope humanity has ever built. For studying objects like Stephenson 2-18, Webb is a game changer. The dust that hides red supergiants is mostly transparent to the wavelengths Webb specializes in. Where Hubble saw vague glows, Webb sees crisp images. Where ground-based infrared telescopes saw blobs, Webb resolves details. Webb has been used to study red supergiants in our galaxy and in the Magellanic Clouds. The results have been striking. Stars that were thought to be obscured beyond detailed study are now showing their inner workings. Dust shells around dying giants are being mapped in 3 dimensions for the first time. Mass loss rates are being measured with precision that was previously impossible. For St. 2-18 specifically, Webb observations are ongoing. Several teams have been allocated time to study the star and the surrounding cluster. The data is being analyzed. Preliminary results have generally supported the large size of the star, though the error bars remain significant. Webb has also been finding new candidate giant stars. Some of them are in our own galaxy, hidden behind dust we previously could not pierce. Others are in nearby galaxies. The catalogue of known massive stars is growing month by month. A few of the new candidates are intriguing. 1 or 2 have been suggested as possibly comparable in size to St. 2-18. None has clearly surpassed it yet, but the surveys are still in early stages. The bigger picture will become clearer over the next few years. There is also a separate possibility that Webb is opening up. The early universe contained, according to theory, stars that were much more massive than anything that exists today. The first generation of stars, called Population 3 stars, formed from pristine hydrogen and helium with no heavier elements. Without the cooling effect of heavy elements, gas could collapse into much larger objects. Some models suggest Population 3 stars may have reached hundreds or even thousands of solar masses. Webb is searching for evidence of these primordial giants. If found, they would be some of the most massive stars ever observed. They would not be present in the current universe, they would have all died billions of years ago. But their light, red-shifted into wavelengths Webb is sensitive to, may still be detectable. If confirmed, these primordial giants would dwarf even St. 2-18. They would be relics of an era when the universe was producing larger stars than it does now. Not because the laws of physics have changed, but because the chemistry has. Heavy elements produced by previous generations of stars now dominate. They cool gas more efficiently. They limit how big a star can grow. St. 2-18 is the king of the current universe. The kings of the early universe were probably much bigger. We just have not seen them yet. The hunt continues. There is a hard ceiling on how big a star can get. The limit is set by physics, not by what astronomers happen to have measured. A star cannot grow indefinitely. At some point, the physical conditions required to maintain a stable star become impossible to sustain. Beyond that threshold, the star either breaks apart or never forms in the first place. For modern stars, in the current chemistry of the universe, the upper mass limit is around 150 solar masses. Stars that try to form with more mass than this experience radiation pressure so intense that it blows away the surrounding gas before the star can finish forming. They self-regulate. They cap their own growth. Once a star is formed, it can swell to enormous sizes during its red supergiant phase. The size limit, called the Hayashi limit, is roughly 2,000 to 3,000 solar radii for typical stellar masses. Stephenson 2-18 sits at the upper end of this range, possibly past it. The star is a frontier object. It may be testing the actual physical limit of how big a stable star can get. Why is there a limit at all? 2 reasons. First, gravity. A star has to hold itself together. The bigger it gets, the weaker the surface gravity becomes. Material can drift away too easily. The outer layers cannot stay attached. Second, energy transport. A star has to move energy from its core to its surface. The bigger the star, the harder this is. Convection can break down. Radiation can be inefficient. The star starts to lose stability. Stephenson 2-18 is right at the edge, maybe past the edge. Some astronomers think it should not exist at its measured size. They suspect the measurements are wrong. Others think the star is genuinely at the limit and is in a brief, unstable phase that will end soon either through dramatic mass loss or supernova. If Saint 2-18 really is 2,150 solar radii, then it represents a kind of natural maximum. Bigger stars may exist temporarily during luminous red novae or other transient events, but stable stars at 2,000 solar radii or above are probably as big as nature can get. In the early universe, the limits were different. Population. 3 stars, formed from primordial gas, may have been able to reach sizes much larger than current stars. The cooling effect of heavy elements limits modern stars in ways that did not apply to the first generation. Some models suggest primordial stars could have reached tens of thousands of solar radii during certain phases. If those stars existed, they were briefly larger than anything possible today. Even larger objects, called quasi-stars, have been theorized. These would be stars surrounding a black hole at their center, with the black hole providing energy by accretion rather than the star producing energy by fusion. Quasi-stars, if they existed, could have reached 40,000 solar radii or more. They would have been monsters by any standard. None have been confirmed observationally. They remain theoretical for now. The largest object you can call a star in the modern universe is something like Saint 2-18. We are essentially at the natural ceiling. It is humbling to look up at the sky and realize that even the largest possible star is dwarfed by other things in the universe. Galaxies, galaxy clusters, the cosmic web. There is always something bigger, always something stranger. The story of Saint 2-18 is not just a story of one big star. It is a story about the limits of what is possible. Stephenson 2-18 is going to die soon. Our sun will die too. Not soon, by any reasonable standard, but eventually, in about 5 billion years, our sun will exhaust the hydrogen in its core and begin its own slow journey toward the end. It will not become a red supergiant. It is not massive enough for that. But it will swell into a red giant, a smaller cousin of the supergiants we have been discussing. A red giant's sun will be roughly 200 to 250 times its current radius. That is small compared to Saint 2-18, but it is still enormous compared to its current state. The sun's surface will extend out past the orbit of Mercury, possibly past Venus, possibly even reaching Earth's current orbit. Earth, by then, may already be uninhabitable due to other changes, but the red giant phase will finish the job. Our planet will likely be either swallowed or pushed outward into a hostile, scorched orbit. After the red giant phase, our Sun will shed its outer layers gradually. It will not produce a violent supernova. It will eject material more gently, forming a planetary nebula, a glowing shell of gas around a hot, dense core. The core will eventually settle into a white dwarf, a small, Earth-sized object that slowly cools over trillions of years. This is not a fate as dramatic as Saint 2-18's. Our Sun will not detonate. It will not produce a black hole. It will not enrich the galaxy with heavy elements like gold and uranium in a single explosive moment. Its end will be quieter, slower, less spectacular. But the basic process is the same. Fuel runs out, star changes, star dies, star returns its material to the galaxy. Studying Stephenson 2-18 helps us understand stellar death in general. The same physical principles apply, scaled up, the same fusion sequences, in a different order, the same gravity, the same radiation pressure, the same convection. By watching how giants die, we learn things that apply to smaller stars too. There is also a poetic connection. Every atom heavier than hydrogen and helium was created inside a star. When a star like Saint 2-18 dies, its atoms become part of the next generation. New stars form, new planets form, new living things possibly form. Carbon, oxygen, iron, calcium, the building blocks of life, were forged in stars that died billions of years ago. You are made of star stuff, not as a metaphor, literally. The iron in your blood was once inside a dying star. The calcium in your bones was once inside a dying star. The oxygen you breathe was once inside a dying star. A future creature billions of years from now, on a planet that has not yet formed, may breathe oxygen that was once inside Saint 2-18. We are part of a chain that stretches across cosmic time. When you look up at the sky, you are looking at distant relatives. The stars that died long before you were born gave you the matter that makes up your body. Their deaths were not ends, they were beginnings. Stephenson 2-18, the biggest known star in the universe, is preparing for its own contribution to that chain. Its death will scatter atoms across the galaxy. Some of those atoms, in some unimaginably distant future, may end up inside a thinking creature looking up at its own night sky, wondering about its origins. The cycle continues. The universe keeps making stars. Stars keep making us. We keep looking up. That is the story of Stephenson 2-18, and, in a way, the story of all of us.